Hello and thank you for watching my video. My name is Astrid Krasniqi. I'm CCNA and CCNP certified instructor. On this video we are covering CCNA semester 2, Routing and Switching Essentials, and this is chapter 1, Introduction to Switch Network. Chapter 1 objectives. Upon completion of this chapter, you will be able to, or you should be able to, describe the convergence of data, voice and video in the context of switch network. Describe a switch network in a small to medium-sized business, explain the process of frame forwarding in a switch network, and then we should be able to compare a collision domain to a broadcast domain. Today's network is changing. Information must be accessed from anywhere in the world. Before, we used to have different type of network for different type of data. So we used to have a voice network only for voice traffic. We used to have a video network only for video traffic, and then maybe definitely a data network for data traffic. So you have to employ different type of technicians for different type of networks. In today's world, because of the devices that are capable of carrying any type of network, now we have something called converged network. That we have one router who's able to do voice or route voice, video or data, doesn't matter. So now we don't have to, we are saving with those devices because we don't have to hire the IT technicians for every type of network that we have in our business. So borderless switch network, like I said, it's called a Cisco borderless network, is a network architecture that allows organization to connect anyone, anywhere, anytime, and on any device securely, reliably, and seamlessly. So now our challenge is to allow people coming from outside with their own devices and be able to connect to our network securely, and we make sure that they meet the health standards that we set in our policies, and they can come to our network. Hierarchy in borderless network. Borderless network are built using following principles. So we have hierarchy. Here we facilitate understanding the role of each device at every tier. So we have tiers, 3 tiers for example, and each tier device has a specific role to do. Simplifies deployment, operations and management, and reduces fault domain at every tier. Then we have a modular. This allows seamless network expansions and integrated services on on-demand basis. Then we have resiliency. This satisfies user expectation by keeping the network operational. And then we have a flexibility. This allows intelligent traffic load sharing by using all network resources. So these are your borderless networks principles. So we have a converged network for core, distribution and access layer. So there are 2 time-tested and proven hierarchical design framework for campus network. First is 3-tier hierarchy, where in the 3-tier hierarchy we have access layer switches, distribution layer switches and core layer switches. Small and medium-sized businesses, they can't afford to have a switch for each layer. So they have at least for them to have at least 2-tier hierarchy model, where you still have an access layer switches and you have a core and distribution layer collapse into one. And this is called now collapsed core layer. So for example, this is very important, the hierarchy, because we have a devices that they work at one tier and only that tier. So we know exactly what is a job they do, and the troubleshooting would be a lot simpler. For example, we have users, IP phones, access points, and all of these, they connect to an access layer switch. Now access layer switches, they don't have to be very, very fast, because they're not going to be manipulating data. Like for example, they don't have to run routing protocols, an access control list and so on. So these can be a layer 2 switches. So port speed, yeah, it's important, but they don't have to run routing. So we can buy layer 2 switches. Layer 2 switches are going to be a lot cheaper than layer 3 switches. At layer 3, we have a distribution layer switches. Here we can do routing and configure routing and access control list and so on. And as well as core layer switches. Obviously, the core layer switches, they want to switch packets as fast as possible. So for us, while you learn in a CCNA, you have to pay a lot of attention on the switching. So switching technologies are crucial on a network design. So switching allows traffic to be sent only where it's needed, in most cases using fast methods. A switched LAN allows more flexibility, allows more traffic management, and supports quality services as well as additional security like port security, wireless, IP phones, and mobility services. Now, when we purchase our switches, we have an option to purchase either a fixed platform or modular platform. Now, fixed platform is like this. It comes as you purchase it from the shelf or from the shop. You can't change it. So if you bought 24 ports switch, it's going to always be 24 port switch. So if you want to add another 24, you can't. You have to go and purchase another switch because these are fixed platform. They can't change. You can't add or remove modules to it. Then we have a modular platforms. These are a bit more expensive, where these ones, they do accept chassis line cards that you can add more ports to it, or you can remove them as you need them. Obviously, these are going to cost you a little bit more. And then we have a stackable switches. So stackable platform switches, these switches, they have a port at the back where you can connect the switches together, and they will behave like one switch. So all configuration you can do in one switch instead of doing them individually. Like, for example, let me go back to this slide here. If you want to connect these switches together, right? These are not stackable switches, so they don't have a port at the back to connect them. You're going to have to connect this port to this port, right? So if I can have a marker, yeah, highlight. Here. So this port, for example, you connect into this port. And then, so you just lost 2 ports. And then if you want to connect this switch to this switch, you lose this port, you connect this to this. So you lost 2 more ports, and then so on. And then if you want to, like, for example, have a redundancy, you have to connect this port, for example, to this port. So as you can see, we are losing quite a lot of ports that we could use them for our users for just to connect those switches. And as we configure in those switches, they will behave independently. So we have to connect, we have to go to each individual switch and configure it. And in the end, they will go through the elections, and they will send messages to each other to keep them up to date and so on. So anyway, low traffic or low bandwidth, just so the switches, they keep each other up to date. For example, with VTP informations and so on. Now, stackable switches are a bit different. With the stackable switches, you are not losing any of the ports in front. You have some ports at the back where you can connect them. So they are like daisy chains like this. So first switch connects to the second switch, then the second switch to the third switch to the fourth, and the fourth back to the first switch. Now these are the stackable switches. Now they will behave like one switch. All configuration will be happening in the master switch, and then they won't go through the elections and all that. You won't waste any bandwidth for them to keep each other up to date with the VLANs and so on. So, role of switches in the network. There are various types of enterprise switches, and the following are features to be considered when we select them. So when we purchase a new switch, first thing that we have to worry about is cost. How much does it cost? Cost of a switch depends on the number of speed of the interfaces, number and speed of the interfaces, supported features. So what is it? Is it stackable, maybe dual power, power points, or does it support power over Ethernet and so on? And expansions capability. Is it fixed platform? Obviously it's going to be cheaper, like I said, or modular platform, which you can add new modules to it, a bit more expensive. Then after we don't worry about cost anymore, we worry about port density. Number of switch must support the appropriate number of devices on the network. For example, there's no point for you to go and buy an 8-port switch if you have 48 users. Power over Ethernet. Some switches support power over Ethernet. Some chassis support redundant power supplies. These switches, they have 2 power supplies. So in case one power supply fails, then you'll revert to the redundant power supply. Then we have reliability. Switch should provide continuous access to the network. Port speed. What is the speed of the port? Frame buffers. Switch should be able to store frame buffers for congested ports. And then scalability. Switch should provide the opportunity for growth. So instead of, if you have I don't know, say you have 20 users, you don't want to really go and buy 24 ports. You want to go and buy maybe 48 ports. You know, you'll have that. Okay, the growth might be in your network. So the fundamentals concept of switching refers to this device is making a decision based on 2 criteria: the ingress port and destination address. So ingress port, it does refer to the incoming packets. The term ingress is used to describe where frames enter the device on a port. And then the term egress is used to describe frames leaving the device from a particular port. So ingress, coming port, egress, leaving. So the switch, for example, here it keeps a table called CAM table or MAC address table. For example, in this example, I'm going to show you, say this PC is communicating with this PC. It makes a frame ready, and on that frame we have a layer 2 information, source address, EE, and destination address, for example, AA. And the switch has built this table. I'm going to show you very soon how the switch builds the table. But as the port comes in, the switch identifies what is the source address at what port it came in. So the source address EE came on port 1. So the switch is going to reset the timer on that port, and then it looks at the destination address, a destination AC, goes back on the table, MAC address table, finds the destination. If it does find the destination, and then it's going to forward it to the egress port. So ingress, as it's coming in, the switch is looking at the source MAC address, and then it's looking at the destination MAC address. Where is it going? Now the MAC address is, if you go to your PC and in the command prompt you type ipconfig all, ipconfig space / all, you should see the physical address. That's your MAC address. So this here, this part of the MAC address is your OUI, yeah? So O organizational unique identifier. Organizational unique identifier. So if we, for example, me and you, we decide to start manufacturing network cards, we need to purchase this. This we can't just give it anything, yeah? So we have to purchase this part. After we have purchased this part, this is, we can start giving our IP, our MAC addresses to the devices. Now, switches use the MAC address table, MAC address, to direct network communication through the switch to the appropriate port towards the destination. For a switch to know which port to use to transmit the frame, it must first learn which devices exist on each switch port. Now, as the switch learns the relationship of port to device, it builds a table called the MAC address table, or content address memory CAM table. Some people call it CAM table, some people call it MAC address table, they're both the same. Now when you turn the switch on, by default the switch does not have any MAC addresses on the table. Doesn't have any MAC addresses on this table. It does have the ports, whatever ports it is connected to, but it's got no MAC address table. So I've got some PCs here. First, let's go through the CAM. Is a special table of memory used in high-speed searching applications. So here I go for some PC with the MAC address tables. Now the MAC address table is abbreviated with just 2 letters. You saw the MAC address table. It's made out of 48 bits, yeah. Now, for example, EE is sending some information to AC. Now EE is down here, yeah. So it's sending information to AC. AC is this PC here. As it's coming in, the frame comes into the switch. The switch, first thing it's going to do is going to identify what port it came in and what is the MAC address of that frame. Then it's going to write down on the table, okay, so MAC address EE just came in on port 1. Okay, I'll keep that on mind. This is going to be in the memory for 5 minutes. And then the next thing he's going to do is going to look at the destination MAC address. Where is he going? Now he's going to AC. Look at the table. I don't know where AC is. Since I don't know where AC is, the switch, what it's going to do is going to behave like a hub. So it's going to send it, it's going to flood it. It's going to send it out of every port, apart from the port they came in. So it's going to send it out of every port. Just try and find that destination where it is. Now, out of the ports that there's something connected to it. It's not going to send it. It's not going to send anything out of this port. There's nothing connected to it. So obviously, out of every port, active port, I should say. Okay, so now BA gets that frame. BA PC here looks at it and says, okay, well, destination is not for me, so it's AC. AC looks at it and says, okay, well, destination is for me, so let me open it further. While AB does the same as BA, just throws it away. Now AC will reply. So it will put the source address, AC, and EE as a destination address. So it looks at, this frame comes in the port on this switch. The switch is going to add the MAC address on that port. So it says, okay, well, I just learned where AC is. AC is on the port 5. now that's 1, 2, 3, 4, 5, 6, 7 in reality, but anyway, just for understanding here, just imagine port 5, and then a destination is EE. So I'll look at the destination. Destination, EE, do I have that on my MAC address table? If I do, I'm not going to do the same as I did before. I'm not going to flood it. I'm not going to send it everywhere. I'm just going to send it directly to the destination because I know where the EE is. So port 1. So for example, now EE, again, this PC is very chatty. It's talking now, this time it's talking to this PC here, AB. Again, as it's coming in, the frame is coming in on the switch. The switch looks at the port where it came in at one MAC address. So MAC address EE, port 1. Do I have it on my table? Yes, I do. But what I'm going to do, I'm going to reset the timer. So I'm going to set another 5 minutes in here. So if it's for 5 minutes, the PC doesn't talk, then it will be deleted. Then I look at the destination. Destination is AB. Destination AB doesn't exist on my table. So what I'm going to do, I'm going to flood it. I'm going to send it out of every port apart from the port they came in. So the AB should get it. The frame forwarding methods, there's two types of frame forwarding methods for the switches. One is a store and forward, and the other one is cut through. Now store and forward is meant to be, it's a bit slower than cut through. Cut through is as fast as it can. Store and forward, what it does, it takes the entire frame in there, inside the memory. It computes the CRC, making sure that there's no, it hasn't been any corrupted. Then it looks at the destination address, and then it forwards it. So that's what it's doing. It's storing it in the memory, checking that it hasn't been an error, then it's forwarding it. While cut through, it's fast. So a switch forwards a frame before it is entirely received. As soon as it reads the destination address of the frame, must be read, and then it can start forwarding. So as it's coming in, you read in the destination frame, destination address, destination MAC address, and it starts forwarding. A frame still is coming in, but it's already going out. So store and forward frame allows the switch to check the frame for errors, so frame check sequence, perform automatic buffering, and a slower forwarding process. So store and forward switches entails receipt of the entire frame up to 9,200 bytes for jumper frames before start forwarding decision is made. So as it's coming in, again, this side here we have a destination MAC address. Where's the pointer? Sorry. This is destination MAC address. So as soon as it reads the destination MAC address on a cut through, it will start forwarding. While store and forward, it takes the whole frames, it stores it in RAM before it starts forwarding. First, it checks the frame check sequence, making sure that there hasn't been any errors. If it hasn't been any errors, then it starts reading the destination MAC address, and then it forwards it. Cut through allows the switch to start forwarding in about 10 microseconds. No frame check sequence is checked, no automatic buffer. So as soon as we read the destination MAC address, we start forwarding this frame. The rest of the frame is still incoming, but it's already outgoing as well, so it's same time. Fragment free. Fragment free is another type of cut-through switching, but the switch now waits for the collision windows, which is 64 bytes, to pass before starting to forward the frame. Collision domain. A collision domain is a segment where devices must compete to communicate. So all ports of the hub belong to the same collision domain. Every port of the switch is a collision domain on its own. A switch will break the segment into smaller collision domain, easing device competition. For example, if we have a hub here and we have 4 PCs, these PCs, they're going to compete for communication. So they will do, what they will do first is they will listen to the wire, so carrier sense, multiple access. They use a protocol called carrier sense multiple access collision detection, which they will listen to the wire, making sure that there's nobody else is communicating. If it's not, they will start transmitting. So one device can send or receive at a time. So for example, if this device is sending, all other devices, they have to sit quietly. Now, hub, it does not break the collision domains. Everybody is in same collision. So if there's 2 devices, they start sending data at the same time, then a collision will occur, and they will find out there's been a collision, which is collision detection, and they will send a jamming signal, so everybody will have to back down and then start again. Switch, if we break this, if we change this to hub to switch, now if we replace our hub with a switch, the devices now, they don't have to compete for the communication. So the switch will break the collision to smaller, will break that collision domain into smaller collision domains. So every active port on a switch is its own collision. Now the devices, they don't have to compete. They just can start sending and receiving data as they wish. So in here we have 4 active ports on the switch. That's 4 collision domains. When it comes to broadcast domain, now broadcast domain is, the switch doesn't break the broadcast domain. If the switch gets a broadcast frame, it will just replicate it. It will behave like a hub. It will just flood it out of every port apart from the port they came in. So it's behaving like a hub with a collision domains. So collision domains, just to not to confuse you, the hub has 1 collision domain. Every port belongs to the same collision domain. The switch, each port on the switch is its own collision domain. But the broadcast domain, the switch does not break the broadcast domain. So every active port on a switch with a default configuration is in 1 broadcast domain. So you need to implement layer 3 device to break that broadcast domains. So broadcast, not a good thing in our network. Okay, thank you very much for watching my video, and please have a look at other videos and don't forget to subscribe. This has been Astrid Krasniqi. Bye bye.